Okay, so we're going to get started with this next session, the title of which is Piecing the Puzzle Together, Part 2. And our first speaker in this section is Peter, who's going to give a talk. And I'm going to get that talk. All right, Peter, take it away.
Thank you. It's my pleasure to be here. I'm Peter Washam. I'm at Cornell University. So I work with the underwater vehicle IceFin, so most of my talks are about that. This one is not. So there's one picture of IceFin, but almost no data from IceFin in this talk, which to me is actually kind of exciting. I know you guys are bummed right now, but I hope I changed that feeling. In your agenda, there's an active in the title. I've removed the active in this to sort of scale back a little bit, but I hope that these data are still very exciting to you. So first off, I just want to thank my co-authors here, Bryce Luce, Hugh Horgan, Brittany Schmidt, and a bunch of others. So Bryce is the brains behind all the noble gases. Hugh Horgan's the brains behind all the geophysics. And then myself and the rest of the IceFin squad just sort of are stumbling our way through how to do noble gas sampling right. But we have succeeded somewhat. So here we go. So another shout out, this data was collected in 2022, sort of 21-22, which, if you recall, was the throes of COVID. So the field team right there did over 5 months that year in Antarctica with 3 quarantines. So it was a bear of a season, and they deserve a big congratulations and round of applause for getting through that. And on sort of the right side of this is Andy Mullen with the rig, and that's just showing how you collect these water samples. And it's very important. You just do it with a Niskin bottle, basically, but it's very important you do it correctly, because if you get any freezing of the water, you start outgassing, and then you lose your information. So you have to be efficient, you have to do it well, and the end result of noble gas measurements is a very powerful tool for tracing not only water masses, but also evidence of any sort of mantle outgassing, which is what I'll talk about. So first off, I'm going to introduce the monster subglacial channel of KM Ice Stream, which Alex Roble and everyone else earlier introduced very nicely for me. So what we're looking at is a map of the Ross Ice Shelf, and the stuff's all washed out, but basically there's an outline of KM Ice Stream. It is stagnant at its sort of lower trunk near the grounding line, but it's still flowing from upstream. And there's these 2 red triangles, and those are 2 identified sort of, you could call them a volcano, but there's sort of some uncertainty of how active they are. So the one that's closer to the pole is Mount Casertz. You might have heard of it. And then the lower one, Hugh, is called Mount Enrica, because there's this paper from our beloved Enrica Cortini, who used to work with us, where she identified the subglacial edifice, and it's sort of a new result, which is interesting and exciting. And what you can't see here is there's these white lines, which are outlines of the catchment probability, which is showing how probable water, subglacial water from those regions is to actually reach the grounding line and flow out into the ocean through the subglacial hydrologic system that is coming out at the Cam ice stream grounding line. And so what you can't see is the upper triangle, Mount Casertz, is in the 1 percentile outline of probability of feeding the grounding line. But Mount Enrica is at, I believe, 30 or 60%. So water does come from that area of the ice sheet and come out into the Ross ice shelf as best as we can predict about 30% of the time that it drains. I believe it's 30. So then in this little insert here, there's a zoom in of the study site. That's sort of the subglacial hydrologic pathway, and then there's these two lakes there, which are the circles. And the yellow star is the new study site, so that's KISS 2, which was in the starting image. And then the white star is the site from 2019, where we drilled through the ice and did some work with the Kiwis then. So, very exciting. This is what the Cam ice stream subglacial channel looks like. It's 255 meters tall. It's about 120 meters wide. It has some strange bell shape at the top. And let's try this. Yeah, I picked the wrong one. That's supposed to be the grounding line, that line right there. So based on our conversation earlier, this is upstream of the grounding line. So yeah, I mean, I could give a whole talk on this thing. I mean, it's bizarre, right? That's in situ data. Basically, they lowered an ADCP as well as an altimeter and spun it around. Craig Stewart did, who's kind of like a magician. And he spun it around several times, and there's actually like a 3D map of this thing. So I'm only showing the 2D cross-section, but it's really cool. And the reason, I'm going to waste all my time on this. I should move forward. But the reason this thing's so tall is because the ice isn't moving. It's just sort of like the ocean's eating away at it. So anyways, the rest, here's the oxygen profile I'll show you later. There's these water samples collected in here, and then here's the flux profiles, which were collected with that setup that I described earlier. So first off, here's sort of Q is a profile of flux, water flux through the channel. So down below, there's a balance, sort of, it's showing how much is going out and how much is going in. Those are supposed to be equal. There should be net zero. So basically we're missing some of the movement of water back upstream, which is probably down there. But still, it's pretty good. A good bit of water's moving through it. A good bit of water's moving upstream of the grounding line. When you look at T and S, well, it's seawater. So seawater is intruding, and there's then this flux of water out, and it just so happens to be low in oxygen, which is interesting, and it has some biological implications of the water that's flowing out. All the stars are the water samples, and this is the wizard data for comparison. And I can't talk about this because I don't have time, but basically the end member of the seawater mass that's feeding this region has something like 20% circumpolar deep water in it. So there is circumpolar deep water accessing the grounding line of the Ross ice shelf. That's a big result, okay? Can't talk about that anymore. All right, so what's exciting, here's neon, and here's delta 3 helium. So this is helium enrichment over background atmospheric values. Basically, the only source of helium-3 on our planet is mantle outgassing, Earth's mantle outgassing. Again, don't have time. The data is about sort of in this outflowing plume and then upper water column. has something like 1.5% subglacial discharge, subglacial freshwater, so that's very high concentration, almost like Greenland level. And the amount of enrichment of helium-3 is sort of like, this is, you could think of a TS diagram, but this is neon and delta-3 helium. And these are the predicted lines from basically mixing with ice melt, and all of this data is way above that. So it's really enriched in helium-3. So what's this tell us? You can convert that helium-3 into a mantle heat content based on the literature, which shows you that there is basically some subglacial heat source that's volcanic. And when you do all that, you can get different fluxes. That's your subglacial discharge flux out. It's low, 3 cubic meters per second. It's nothing super exciting, but it's definitely within what we would expect. Again, the oxygen signal, if you're interested, I'd love to talk to you about it more later. I don't have time. The ocean heat flux, now moving out and in, there's a lot of heat from the ocean moving upstream in this channel, 357 megawatts. The geothermal heat flux out, and there's some interesting story with maybe a recirculation up, is only 24 megawatts. So that's like a dormant volcano. That's the heat flux. But what's cool is you can get this area heat flux doing a couple things. So it's like 108 milliwatts per meter squared, which is above background levels, and this is purely a result from volcanic outgassing. So this has nothing to do with just background geothermal heat flux out. And I'll just leave that question up because I'm 2 minutes over. So thanks.
Okay. Let's move on to our next speaker. Yeah, please.
Hi everyone, my name is Jacob Anderson. I'm a postdoc at Lamont. And meet some new people here as well. This work builds on work we did with the New Zealand program, and I've also taken some of these samples to continue my postdoc at Lamont as well. So I'm going to kind of be presenting some old information, and then also what we've been doing, or what we hope to do next year as well. Okay, so when we're trying to reconstruct the grounded marine-based ice sheet in the Ross Sea, there's kind of a couple of ways we can do that. One is collecting marine sediment cores to tell us when the grounding line retreated, and that gives us an insight into the physical grounding line position. The other is to go to the margins of the transantarctic mountains or anywhere where there's rock, and we can then get the elevation using cosmogenic exposure dating. And Roger this morning kind of did a nice overview that set the scene really nicely for what I'm going to be talking about as well with respect to reconstructing past extent of the ice sheet. The other thing that we can do is use geophysical evidence to look at topographic highs or other areas where you may have pinning or where ice may tend to stick around. And all of that is used to benchmark the models, and so the models rely on that proxy information to reconstruct or to test how accurate their models are. The big challenge is there are large gaps, and the data is very fragmented. So we have these huge knowledge gaps in our reconstructions. And you can see here, so we see this retreat occurring in the middle of the Ross Sea first, and then on the margins it sticks around where there's these pinning points. You can imagine they're a little bit like nails and holding back the ice and kind of reinforcing it on the edges. So they're kind of like a reinforcement, if you like. The other challenge is there's still disagreement with respect to how the ice flows and the contribution from the East Antarctic ice sheet and the West Antarctic ice sheet Some argue that the grounded ice sheet kind of plugs some of these glaciers and they're effectively blocked. The other argument is that there's active contribution from some of those East Antarctic outlet glaciers as they flow into the western Ross Sea. So I'm in particular interested in the McMurdo Sound region and at the western Ross Sea. So here you've got Mount Discovery and Minna Bluff and Ross Island, which kind of stick out a little bit from the Transantarctic Mountains. And that's really interesting because what we see from a lot of the outlet glaciers is they tend to show a signal of retreat. When the grounding line retreats south of their position, that's when we see the outlet glaciers start to lower. These volcanic peninsulas and islands give us a more representative example of how the marine-based ice sheet in the Ross embayment is responding. And so the area we're really focused on is Mount Discovery, which I'll be talking about now. So this is previous work that we've done, and basically there's this fantastic granite clast-rich drift sheet which marks the upper limit of the ice sheet during the last glacial maximum. And that's about 500 meters elevation today. And so we can go to these sites and then we can collect these large boulders, perfect targets for surface exposure dating, rich with quartz. And we collect the tops of these boulders, and they give us our exposure record. And so we had a helicopter day to get to this 500-meter upper limit, but most of our work was restricted to the lower reaches of Mount Discovery. And so we have this gap in our record. And for those of you who are still awake in this afternoon session, you'll notice that these ages don't quite match up with the figure. That's because they've been recalculated. So we're using a new scaling scheme and production rate. But basically, yeah, we have the initial the onset of deglaciation around 14,000, and then we see this retreat history. But there's this big gap between 500 meters and 250 meters where we don't know the rate of retreat. And so there's kind of two different scenarios. And so what we did last year was we went back to that point, and then we walked down from 500 meters to 200 meters to collect a series of samples for exposure dating. We haven't got those ages yet, but there's two scenarios that we expect to see when we get those ages next year. One is a slow thinning scenario, and the other is a rapid thinning scenario. And I'll just talk about the rapid thinning scenario for the next few minutes, just to demonstrate how this compares with other sites and potentially with contemporary rates. So if we do have a rapid thinning scenario, you can imagine between 10,000 and 8,000, you have 500 meters of lowering within 2,000 years, which is a rate of about 0.25 meters, 25 centimeters per year, which is kind of consistent with the upper bound here. It could be faster than that, I think, potentially. If we have this really rapid retreat scenario, you say you could lose 500 meters in 1,000 years, then maybe it's 50 centimeters per year. Those rates compared to Richard Jones' work are pretty consistent. So if we have a rapid retreat scenario in Mount Discovery, then that would be somewhat similar to Gondola Ridge, which is this blue line here. It may be a little bit difficult to see. And this is a high-density data set, so we've got very high confidence that the range is somewhere between 30 and 80 centimeters. They also have this low ridge site, which is lower density, so the confidence isn't as great, which is why there's larger range there. But the average of that is also pretty consistent with Gondola Ridge. So it's probably somewhere within the 50 centimeters per year. Compared to contemporary rates, it's much lower. So even if we take a rapid retreat scenario in the Ross Sea, from the western Ross Sea, it's still significantly lower, and there's probably some people in the room who are more familiar with contemporary rates of retreat than I am. So please let me know if there's different values from Thwaites and Pine Island or anywhere across Antarctica for that matter. But the important takeaway here is that throughout the Holocene, these rates of retreat are a lot lower than contemporary rates. The other piece of work where this is really valuable is data model comparison. There's a large data mismatch, and so if we take those two sites, Mackay Glacier and Mount Discovery, alongside the model here, the model does a pretty good job at reconstructing the rates of retreat, but again, we don't have a lot of information to really tune the model and test it or benchmark it against some of that work. So our goal is to get this really nice high-resolution retreat chronology, and there's very few sites in the Ross Sea that can capture the onset of deglaciation all the way to the ice sheet lifting off and becoming a floating ice shelf. So this is a really unique site, and we're really excited about the high-resolution deglaciation chronology here. So just to kind of moving forward, really we're about constraining these fastest periods of retreat in the Holocene and comparing them with the contemporary rates, reducing uncertainty with high-density results and potentially identify some of these climatic events that may have been occurring as well. Improving the data model comparisons, so working with the modeling community. What this work doesn't do is it doesn't tell us what's happening in the middle of the Ross Sea, so that's still a big question mark about what happened in the middle compared to on the margins. And just lastly, this is really cool for outreach. In Greenland, we've got this 3D model that's been printed, and you can remove the ice sheet. And it's a really fantastic way to demonstrate to people what's underneath the ice. And we're currently working, Isabel, who's here as well, we're working on developing a similar 3D printed model for Antarctica. So hopefully we'll have some of those developed next year as well. Thanks.
Can we get all of our speakers back up here, please? This is a really great series of talks. Thanks. All right. Ellie.
All right. Hi, everybody. Thank you all for your talks. My question is specifically for Jacob. I know you mentioned the possibility of a fast or slow retreat scenario, but I was also curious if you could have considered a retreat re-advance scenario, since that's been supported by a lot of work on the Saipo coast.
Yeah, the re-advance probably doesn't make its way that far north, and Reed probably has a better answer than I do here. And we have also got a series of ages on the ice shelf that are younger than 7,000, and so it's not out of the question that you could have that, and C14 would also be helpful for that. And I forgot to say as well, we also are planning on doing C14 above the drift limit to see if there's actually any cold-based processes that may have, salt and pepper sprinkled younger clasts above the drift limit as well. But typically above that drift limit, the boulders are a lot more weathered. But yeah, Reed, do you have any comment on how far the advance may have been in the Ross Sea?
Yeah, it's hard to say just how, that was a good question. It's hard to say just how far the advance was, but it's pretty clear that it didn't represent a huge elevation change that would be reflected along the coastline in a way that would be particularly easy to measure. So, good question though.
Not a question again, sorry. I just wanted to thank Brian for pointing at an older publication, the Denton and Hughes, and Reed for, there it is right there, the list of names on this, early workshop. I think it is important to think about the foundation. I think one thing that'd be good for early career folks in here is, thinking about what we know and how well we know it. I think that second part is equally as important. I think one of the good places to go for that is, I pointed to the strategic document that actually shows a lot of what we know now and how well we know it. And these are questions I think we need to carry forward as we go into the next strategic document. This is so key. So thanks for bringing that up. And now maybe a question, how do we move forward? I think that how well do we know it is a really key question as we go forward. And I'll just leave it for comments from you guys. Sorry.
Thanks, Kelly. I'd like to add continuing to press our knowledge and find signal in the noise. Because I think a lot of the old records are often kind of cast aside because we've learned new things, or we've caught on to some new trend, or we've taken the top 10% out of our data and moved on. But I think that there's actually quite a lot that we can gain by just digging into these old data and doing what Kelly says, by continuing to poke holes in what we really know and how well we really know it. I think Reed's gonna talk here, but one thing I'd like to say is that one place that my group is really thinking about this today is with marine radiocarbon data. So especially in this community, especially in the Ross Sea, we have looked at a ton of marine radiocarbon data and done a ton of marine radiocarbon dating. And often we see old ages and we just say, okay, this age is old, we're done. And I see Brad Rosenheim in the back here, and he's done the lion's share of the effort in this community by showing us that we can throw new methods at these old samples. But something that we're trying to do in my group is find signal in the noise of those old data and not just cast them aside. So if you're interested in that, go see Joe Ruggiero's poster after this and see how he's finding signal in the noise.
And talk to Anne Gruneau if you're interested in exposure dating or other things. There's a fantastic resource at Ohio State. I'm sure Ian Dial cataloged very carefully every rock he ever picked up, and all of the others that are in the collection. I'm sure they're gems that could contribute to this data set. And I want to point out one of the hardest things for us to establish on the paleo side is always kind of the most important question and the hardest one to address, which is rate of change. For years, people throw out the word, West Antarctic ice sheet collapse without defining what that means. How far does it have to be? And importantly, how quickly does the retreat have to be for it to be a collapse? And the actual rate of change, we heard a couple of talks that touched on rates of change, right? But that's something we always have to remind ourselves is really, really important and hard to constrain.
Following up on that and the legacy data question, this is more for the paleo folks. We've been talking about international collaboration as a thing that we think is valuable, and especially looking at the distribution of ICE-D data and knowing that the U.S. Has easy access to some sectors of Antarctica, but harder access to other sectors. Do you have a sense for, of all, say, the Cosmo rocks or other data sets out there, what fraction could we access in US administered repositories versus how much of that would we need to do international collaboration on the legacy data front? And have you thought about that sort of project?
So I think the very special thing about ICE-D is that anyone can contribute to it. So it's not like a specific repository where you have to be funded by a certain place or live in a certain place or work in a certain place. Anyone who does cosmogenic nuclide work can contribute to this database, so that's super cool. In terms of like what we have access to in the US community and where we need to reach out, like there are very obvious places there. We have like tenfold grown our knowledge of the Amundsen Sea embayment through the International Thwaites Glacier collaboration because of work that originally Mike Bentley started, then Joe Johnson led as part of ITGC. And we would not have had access to that sector if not for the British Antarctic Survey. So we need to continue to work between our programs in ways that are maybe a little bit more sustainable than ITGC to get out to these places. And I'm sure you can talk more about New Zealand connections and places we can get to there. But I think like there are also polar rock repositories in the US and in other programs. So we should start reaching out to our collaborators in those programs and see what they have.
Yeah, just on that, and I think there's so many samples across all of Antarctica that, as you pointed out, have been collected for largely for beryllium, and it would be amazing to just reach out to these people with these archives all around the world. And the only restrictions would be, sending the samples on FedEx or whatever, and then running them. So there's hundreds, thousands of samples across Antarctica to do this, just waiting to be measured. And I think there's a real opportunity to do a full suite of C14 just by connecting with people around the world who are happy to just send their samples. Yeah.
Yeah, thanks for saying that. I think one of the really cool things is that we've gone around and we've picked up all these rocks, and so many of them were picked up before we could even extract in situ carbon from rocks. And now we have that capability, and who knows what other methods are coming online. So that's just a plug for don't keep rocks in your basement. Please send them to Anne.
I have a question for Peter. So the CAM channel is partly so large because clearly it's being melted away and there's not much ice advection to replace that, right? But that doesn't mean that there aren't other places where you might not have such a obviously large channel, but where a lot of ice loss and basal melt could be occurring just in a fast flowing regime. So how do you think we should go about finding those places? So if we want to drill in more places, prioritize where we're going to drill in more places and send ice fin or do sampling, how should we find those places?
I mean, the map, the hydropotential routing map landed right on the channel, so that's a good start. Obviously, there's a lot of radar data out there that shows ice shelf channels. Many ice shelf channels are fed by subglacial channels. I think, oh man. I think there's a lot of different ways to go about it. So obviously surface elevation change too. So I think the way they found the channel for the Mercer, is it Mercer? It's the Ollie Marsh paper. I think it started with remote sensing and watching surface elevation change. So I think you have a lot of different ways, but at the end of the day, someone's got to go there and drive or fly some radar lines to confirm that it's there. And yeah, until you do that, it's not worth drilling because you'll miss it probably. So thanks.
Just want to add one thing. You mentioned in your talk that there's another bit of data. We only had 2 samples, so we didn't have a paper unto itself, but it was sort of buried in the retreat and reinvents paper, is that we also had iodine-129, which is a bomb-produced isotope. So that means some surface water has made it all the way back there as well.
To Wizard?
Yeah.
No CDW at Wizard. Only CDW at Cam 2, which is really fascinating because there's no CDW at Cam 1, which is 50 kilometers away. So there's some ridge that's separating that side of the Sibel Coast from the other. Yeah, I mean, it's really, as an oceanographer, that just jumped out to me. But that's cool. I mean, maybe that's evidence that the Plinia didn't completely erode the Antarctic surface water signature for you. Yeah.
But that little bit of data just kind of gets lost because it's just two dots in supplementary materials, but it's worth mentioning. Yeah, the Wizard noble gas data Bryce had sitting around, and he was kind enough to send it over. So
Let's take these last two questions.
You kind of just answered my question, which was how far inland do you think the CDW can intrude in the CAM channel? But kind of taking that further, do you think the CAM channel can tell us about the conditions under which CDW intrusion can occur along those channels? And yeah, I guess kind of related to Alex's question about the ice, the stagnant ice, and lack of mass replenishment. But yeah, just expound upon your previous discussion, please.
I'll try to be quick. So 20% CDW, there's mixture of glacial melt and subglacial freshwater in that bottom sample. So it's only minus 1.7 degrees Celsius. It's not warm. But the fact that there is a CDW signature in the water near the seafloor there is about 0.1 or 0.15 degrees warmer than 50 kilometers away is a big signal when you think about melt on the Ross Ice Shelf. So, I mean, any channel that's small, you're going to constrain your flux out if it's strong. So it's going to be moving at a faster rate. So one of the things that happened at this channel, as far as I can tell, is there's big outwash events that eroded it to the height that it is. But honestly, if you look at, this ice shelf channels, you can tell if they're in a warm cavity or a cold cavity by their width. If it's a wide ice shelf cavity, it's in aspect ratio, not just width, aspect ratio. If it's wide and tall, then it's in a warm cavity. This one is very narrow, which means there's not that much difference in lateral and vertical melt. So the influence of that seawater on driving melt and really growing this channel is showing up as not that important as far as widening it. And there's just these big outwash events where you get that turbulent heat flux up, and that's what's grown the thing so tall.
I actually have two questions. One is for Ryan and one is for Reed. In that study, you speculated about the extent of the last glacial maximum, and this morning I mentioned we had this 2011 science paper where we basically took Peter Clark's data specifically for Antarctica, but with the exclusion of cosmogenic isotope dating, and added our carbonate shell dating, and we came to the finding that the LGM started somewhere between, if I remember it correctly, 29 and 27,000 years, and ended right at 19,000 years, which is part of why we had the title in the paper, Interhemispheric Correlation. I don't know exactly the title, but it was like this, because it was so similar based on that data, which is a little bit different than what you say. What do you say to this? So.
I think my point is more that LGM is being used as a kind of a catch-all term, and we need to think a lot more deeply about what local LGM means, because all of the sites that we have constraints from are feeling the LGM differently. And when we only have a couple of sites around Antarctica with good constraints, we can't really make these big swinging conclusions about when the LGM is. So it's more of a call to action to think a little bit more deeply about what the LGM means.
I mean, we even made the remark that in the Ross Sea, it's more like 14,000 years.
Yeah.
So, you know,
No, I'm familiar with the work. It's
later
awesome.
than that, so. And one question for Reed. I was a little surprised that MIS 11 doesn't really stick out that much. You said it's like 13 and 15 is so much warmer. Is it like this transfer out of these lukewarm inner glaciers? I don't really know why they are so distinct.
Well, yeah, stage 11 was warm, but it, according to the calculations for my group, it was warmer in 13 and 15 and even 14 a little bit.
That's
so,
very interesting.
Yeah, 11 wasn't huge, and 5 was doing some funny things we could talk about later. The other thing that didn't show up, which maybe it was a diagenesis thing, but stage 31 didn't really show up in the Amundsen Sea as anything.
Yeah, it doesn't really show up in Iceberg Alley that much.
Yeah, in the Ross
either.
Sea it was massive.
Yeah. Okay, thank you.
Let's do one very fast question.
Sure, thanks. I have a question for Peter, which is about subglacial channels. And so the CAM channels have been talked about a lot, but there's a number of large channels that are somewhat similar in scale in the Transantarctic Mountain outlet glaciers, Beardmore and others, also in cold ice shelf cavities. There, when you look at the total catchment subglacial water flow, it's inadequate to promote the formation using a simple plume model or even a 2D plume model of one of these channels, when sometimes we find 10 across the grounding line. And so I'm curious what your opinion is. There a fundamental disconnect where we're underestimating the subglacial input into the system for these outlet glaciers, or are we missing something about the ice-ocean interaction that can drive these large channels to form for the Transantarctic outlet glaciers?
I'm definitely more comfortable with the ocean side of it, so I'll comment on that, and then you and I can talk more after. So they're grounded deeper, so it's not just a question of ocean temperature, it's the pressure depressed freezing point. I mean, bird has high melt rates, so like you can grow a channel quite quickly if you're at 1,000 meters depth, even with high saline shelf water, so it's like a 1 degree thermal forcing or something like this. That site had something like a 0.4 degree thermal forcing, so high for the Ross, but not quite that high. But I could talk more after if you'd like.
Yeah, even using some of this, even taking that into account, there's just so many of them that I think it's surprising in the cold shelf cavity, even the grounding lines are relatively deep, and they're clearly visible. And the Broke has an excellent paper from about a decade ago that identifies several of them, but if you look at the detailed surveys, Paul Winberry has been part of one of them, there's many, many more, so it's just an impressive number overall that I'm not sure we fully understand the reasons for.
Great. Thanks so much for a great session. Let's thank our speakers for their talks.